Okay, welcome back after coffee session. And first presentation will be by Neil Kamal and Malik and Raghunath Sahu from IIT Indore, and it will be on JEP side tagging at Large Hadron Collider experiments. Over to you.
So thank you. Good morning to all of you. In fact, it is a switching over from CMS to Alice, but on little phenomenology side. And organizers told me that we should make the session little informal. And to make that happen, so in fact, I should tell you a little bit of history, which way we started. And it is actually a great pleasure to see so many of high energy physicists using machine learning. And initially, we started thinking in Alice, we are the only group from India. And when we published our first paper in Physical Review D in 2021, when I was a CERN scientific associate, and I took the paper to our physics analysis coordinator, he didn't appreciate it. And then I had little discouragement, thinking that possibly this may not be a good area. But we continued, and we published 3 papers, consecutive papers in Physical Review D. And the topic we have chosen today is essentially the fourth paper, which is in archive. And we have chosen this particular one so that data are in hand and we can give you a hands-on. So it is not a new problem. It is already in archive. But essentially, this is to look into ZEPSI prompt versus non-prompt production, and milled rapidity versus forward rapidity particle production mechanism difference, which we found from Alice experiment. And we are trying to resolve that, which is not yet explained by any of the perturbative QCD models in the market. So this is the topic we have taken. Now over to Nilkamal, and then I will come in when it is required.
Okay, so hello everyone, good morning. So today I'm going to talk about heavy ion collisions, quark-gluon plasma, and quarkonia. So the JEPSI tagging and where do we apply machine learning techniques in that. And my collaborators are Mr. Suraj Prasad, who is over there, and Professor Raghunath. Okay, so I will give a brief introduction to heavy ion collisions, then quarkonia production, the project proposal itself, that is the tagging of JEPSI, outline of the project, and some bonus content at the end. Okay, so to create quark-gluon plasma, which is a thermalized medium of deconfined partons, we have to produce this quark-gluon plasma in the lab. So we take heavy ion collisions as our probe. So what we do is, as you can see in the diagram, we have 2 Lorentz contracted heavy ion nuclei which collide. And due to the high energy density that is deposited at the collision point, we can create a deconfined media. As we know that due to higher energy scales, interaction weakens. That is known as the asymptotic freedom. And that thermalized plasma can then evolve through viscous hydrodynamics. And this inelastic collisions among the partons can lead to can also lead to produce of hadrons. And in between, there is a mixed state where both partons and hadrons coexist. And after some time, when the firewall expands and cools down, we have a chemical freeze out. That means all the partons are now converted into hadrons. And then these hadrons can again go through hadronic rescattering among themselves. And after a certain temperature, we call it kinetic freeze out, where this elastic collision between these hadrons ceases to exist. And we have the final particle spectra. That means their momentum is fixed. And then we have the detector sitting around, which can take the beautiful data for us. So now you can look into these 2 pictures over here. First one is the proton-proton collisions at 13 TeV root test energy. And this is the lead-lead collision at 5.02 TeV. These are 2 realistic event display from the Alice detector, which is one of the detector dedicated for the study of quark-gluon plasma at the LSC. Okay, so next moving on to quarkonia production. So quarkonia basically refers to the heavy quarks and anti-quark pairs, basically CC bar and BB bar. Heavy quarks are actually good probes to study QGP because due to their high mass, they are basically produced very early in the collision because, due to these partonic interactions, and they evolve through the QGP, and they have faced all the phases during the evolution. That's why they are very good probes to study the medium as they interact with the medium during the evolution. In proton-proton collisions, however, we can also study the production of heavy quarks. This is known as vacuum production because there is the QCD formation is not anticipated. So the initial creation is a PQCD based process, and the evolution to a bound state is a non-perturbative QCD process. Now, to validate both perturbative and non-perturbative domain of QCD, this Quarkonia is a very good probe. And at the experiment at the LHC, different experiments actually have studied this Charmonia production in proton-proton, proton-lead, lead-lead, and so on collision systems. Okay, so a little bit about the detector itself, which is the Large Hadron Collider experiment, ALICE. And you can see the detector here. The point of showing the ALICE detector here is that it has a dedicated muon arm in the forward rapidity region, this entire block which you see. And this muon arm is very essential because we have lots of mesons decaying into this muon channel. And one of them is the JEPSI, which is the CC bar bound state. So ALICE provides excellent opportunity to study this JEPSI, Psi2S, and also Upsilon productions, which are the BB bar bound states. So that's there. And right now we are in the phase of run 3, as already the collaborators from CMS have explained. And we are achieving unprecedented energy at 5.36 TeV for lead-lead and 13.6 TeV for proton-proton collisions. And also there are plans for proton-oxygen and oxygen-oxygen collisions in the next year. I was fortunate to participate in the run 3 data taking this year. And this was a picture of the ALICE site in Saint-Denis, Poly, France, which I took during my visit. Okay, so another signature. So this quark-gluon plasma, due to the strong interaction, quark-gluon plasma is very short-lived. So we have to look into some indirect signatures to study the properties of quark-gluon plasma. And one of them is the Charmonia suppression. So in the presence of quark-gluon plasma, the production of Charmonia is greatly altered. So how do we know that? Because due to the presence of high density partons in the medium, and as they are interacting, they're thermalized and they're interacting, the color force that is responsible to bind these bind the quarks into hadrons is screened due to the presence of these deconfined partons. That means we have enough partons, but they are not bound, they're not getting bound to form the bound state of JEPSI and Psi2S. And this process, this phenomena is also known as melting of Charmonia in quark-gluon plasma or Charmonia suppression. And this can experimentally be found with this nuclear modification factor. So this is a very simple analogy. You can understand that in the numerator we have the yield of JEPSI in nucleus-nucleus collisions, and in the denominator we have the yield in proton-proton collisions. So basically, if we think that nucleus-nucleus collision is a superimpose of many proton-proton collisions, and then we can multiply the number of binary collisions, then this ratio should be equal to 1 if there is no medium effect. So RAA should be equal to 1. But in reality, what we observe is that RAA is less than 1. That means there is a suppression in the yield when you go to the nucleus-nucleus collision systems. So this is an indirect signature of presence of quark-gluon plasma. And you can see the Psi2S yield is even more suppressed because it is heavier, it is weakly bound, and the size of Psi2S is more as compared to JEPSI. So with this different idea, let's move to the problem itself. So this is topological production of JEPSI. So as I said, JEPSI is a light charm vector, which is a bound state of CC bar. And it has decay modes in electromagnetic channels, that is mu plus mu minus and E plus E minus. In ALICE, we have this muon tracker and muon spectrometer. That's why we look into this mu plus mu minus channel. So there are two ways in which JEPSI is produced. One is the direct production. That means the CC bar pairs are produced initially through these partonic interactions, or feed down from decay of higher charmonium states. Like the higher charmonium states are produced and they decay to JEPSI. So this process is known as the prompt production. Another channel is the non-prompt production. So non-prompt productions are CC bar pairs coming from beauty hadron. So we know that one quark can go to another, it can change flavor through weak decays. So these beauty hadrons, which is BB bar pairs, they can decay to CC bar through this weak decay channel, and they can also yield JEPSI. So this is known as a non-prompt. But in a formalized measurement, in a bulk measurement, we have this challenge to identify prompt versus non-prompt production of JEPSI. And there, actually, we want to apply this machine learning model. So here, just a schematic diagram. So if this is the interaction vortex of two nuclei colliding, then there are two possibilities. One is your direct production or prompt production, jet size shifting to some distance and then decaying to the lepton pairs. Or it can produce a beauty hadron and then it can decay to JEPSI and then JEPSI decays to this dilepton. So obviously we do not have the PID for JEPSI directly. What we do is we take the dimuon invariant mass and then we can reconstruct the JEPSI peak around its mass and then we have a small peak for the sideways. Okay. So now, what is the conventional method? This is not the new study somebody is doing. There is already a conventional method through which they can identify the production of prompt and non-prompt. So what they basically do is, this is the dielectron channel invariant mass spectra, and this is the pseudo-proper decay length. So what they do is, if you can look into here, this vector joining the production vertex of JEPSI and the primary vertex is known as the L. So this L can go as input here, and then you can put the mass, and you can calculate the quantity known as C tau, which is known as pseudo-proper decay length. And if you have the profile, you can see that the prompt has a different profile. The non-prompt, like the yield coming from non-prompt decays, it has a different profile, this pink one, and then there is a background, obviously. So what they do is they try to calculate this probability density functions known as this F for prompt, and from B is from B to decay. These from Monte Carlo fittings, and from there they can calculate this signal function, and then they can fit into this function over here, where the unknown quantities are this F signal and this FB. FB is the ratio of non-prompt to total production, non-prompt to inclusive production. So this is the statistical fitting method, and here you can only calculate this production fraction, but you cannot say at the dimuon pair level whether it is coming from prompt or non-prompt. So that can be an interesting problem to resolve using machine learning. So I don't go much into details of machine learning because everybody knows about it, and we will be discussing something called as this classification problem. And we have several sectors where machine learning has been implemented, and there is a very good web page you can go and check. There are more than 750 papers or close to 800 papers now in high energy physics, and I'm talking about the heavy ion physics and QJ phenomenology. Okay, so the project outline. So what we do here is we have to train the model, obviously. So what we do is we take Pythia event generator and we can generate prompt and non-prompt JEPSI separately in proton-proton collisions. We can store their decay topology and their tags because we know from Monte Carlo where they are coming, their mother particles and everything. So we can store it. And then we have the 3 tags: prompt, non-prompt, and the background. Because first we have to identify the signal, and from the signal we have prompt and non-prompt classification. So basically there are 3 classes. We store these opposite sign dimuon pairs, and there are some necessary things like invariant mass, transverse momentum, rapidity, pseudo rapidity, and of course this pseudo proper decay length. So all these informations can be taken as the feature of the model. And another thing is that we have to compensate for the class imbalance. As you can see, the production cross-section of prompt JEPSI will be higher as compared to the non-prompt. So there is a class imbalance. So we have to take care of that. Otherwise, our model will be highly biased towards this prompt production, and it will misclassify the non-prompt. If at this point a dataset is provided to you, then you can train a boosted decision tree or neural network or something else to achieve the goals, like classifying the JEPSI. And you can plot the classification accuracy, confusion matrix, training, and validation curves. So this is basically the outline of the project. And the bonus content is if you can compare it to the data. So here you have this production fraction of non-prompt. So as you can see, we have Alice results. We have tried to use XGBoost and LightGBM. So you can see that we can go on much differential in PT because we can identify directly the dimuon pairs. And you can see that there is a plateau here, and then we have a increase, and then again there is a plateau. But that cannot be seen with the existing data points. So that means it takes you another step ahead to understand the production of non-prompt in proton-proton collisions. And obviously this can be scaled to lead data as well. So this is all about the project. Thank you very much.
Questions?
Number of features?
Yeah, what are the number of features for?
Right now we are, okay, so we make it experiment-like because we want to apply this method in experiments. So what observables we can access from the experiment, from the detectors, those are actually used. So here we can have the dimuon invariant mass, their transverse momentum, their rapidity, and one of the crucial thing is their decay length, pseudo-proper decay length, which is evaluated using this expression. So these are the features.
So these are what you directly get after reconstruction. You don't create a, I mean, a combination of these variables into some higher level features, or you just directly pass on these like lower level features to your.
Yeah.
Okay.
Hello. Yeah. So here the L vector, like, this basically exploit the impact parameter from the collision vertex, like,
No, that is not impact parameter.
Okay.
So this L vector is the shifted vertex. So this vector, which is giving the distance between primary vertex and the Jepsi production vertex. This length.
Yeah.
This L.
So my question is, like, apart from this, like, shifted, like, in the space, I mean, so this JSI is produced inside a jet. So probably the lepton that comes outside, like, from the decayed JSI, they could be, I mean,
So
they could be non-isolated also, right? So have you looked at their isolation properties also, like?
We actually, in QGP, actually, we are more interested in the bulk properties. So basically, we don't go into each identified Jepside jets. Rather, we study their production as a whole. So studying more differentially with jets, we don't do that. I mean, we have not done yet.
So this JEPSI is not part of a jet. So it is reconstructed using the spectrometer, muon spectrometer from the dimuon channel.
Okay.
And the results are also compared with the mid-rapidity di-electron channel for the production mechanism difference. So we have not taken any consideration of JEPSI in jet. So I think that is the next step ahead. What do you mean by isolation properties? I mean,
So you are talking about classifying JEPSI, which is produced inside the jets to the
yeah, it is jet in medium property. So that is a bit different what it's talking about.
Well, this JSI is produced inside a jet dominantly. So isolation does not help so much.
Experimental.
Okay, using these conventional methods or the new one? It is hard to say because these templates are actually found from the Monte Carlo itself, and then we are assuming that the data actually follows this template. So that's why the efficiency cannot be. I mean, you just don't know what is the fraction. I mean, theoretically you can estimate, but then your model, there is a model dependency. So it's hard to say.
So in data, presently you cannot distinguish.
No, they just, what they do in data is, no, they distinguish, but what they do in data is, they assume that these templates, what they get from Monte Carlo is correct. And then using that, they can get this fraction, only the production fraction. And then if you know the inclusive cross-section, you can multiply this production fraction there, and you can find the production cross-section for the non-prone. That's what they do.
Thank you.
This is definitely not event by event, but what we are doing in machine learning is event by event. In even track by track.
Yeah, just to add to.
We have to stop here. Okay, so
Yeah,
Okay.
just one line just to add, Kumar's question. So for example, in Monte Carlo, if you are using Pythia, so this is a model, right? And we see, if you look at the final results, none of the PQCD models explain the data. So that is why there is a little model bias. Okay.
Next is me.
Hello. So next presentation by, okay, Amir Subba and Ritesh Singh. So they are talking about the flavor tagging, the hadronic decay of W.
This is the okay. Hello. Yeah, I think I'm audible, right? Yeah. Okay. Hello and good morning. My name is Samir, and I will today I will briefly talk about light flavor tagging in context of polarization and spin correlations. So to start with, I think most of you know, like this is the WW production in the electron positron collider. So if you see, like the production part, right, up to the WW, this can be like if this can be explained, or you can find out the dynamics of the production part via matrix element calculation, right? And so basically what I'm trying to say is the production part can be explained in this density matrix, right? Where it's a function of your matrix element, right? So also you can parameterize your density matrix in terms of this identity matrix and polarization vectors and your tensorial components. Okay. And as I've told you, if you expand this density matrix, you'll basically get 3x3 Hermitian matrix uh, where the element of those Hermitian matrix you can actually find out by doing the partial integration of your decay distribution. Okay. So decay distribution, if you want to see, like if the first part, if you see the production part, you will explain this via the density production density matrix, and to accommodate the decay part of the W, you'll explain via the decay density matrix, right? So if you take, if you do the combination of these two matrix, you will end up getting a distribution of the final fermions from where you can get the element of each density matrix as this form. So eventually, the element of each density matrix boils down as a counting procedure, right? If you see here in the form of asymmetries, okay? So if you look into the two spin one bosons, then you will end up having such observables, right? Where the observables in the red, as you can see, these are what we call as the flavor dependent observables. It means, right, to reconstruct them, this excuse me, these observables, what you need to know what is the daughter of your decay of your resonance. Okay, if you don't do, then this the value of these observables averages out, but the observables in the blue are the flavor independent part. That means even if you don't know the idea of your daughters, you are fine to work with it. But we have found that the most of the contribution to the chi-square comes from this red one. Okay, and also you can classify these observables in terms of whether they are CP even or CP odd. As you can see, these are labeled as E and O, right? Okay. So now, as I've said, as I've told you, that this red one requires flavor tagging. So for that, what we construct is features from the jets. Some of the features that we use are this number of visual particles, number of kaons, their transverse momenta, normalized energy, pions, number of leptons, hadrons, displaced tracks, right? You can have a displaced track if you have a particle like short-lived kaons or lambda baryons, right? And if you look into the correlation table, these are the correlation table for some of the features, right? You see here, this is the jet energy of the jet. This is the PT of the jet. The energy of the jet is having a huge correlations, right, with the class. And similarly, if you see here, right, the P jet of the pions, or these are the scalar momenta of your pions. These are having some huge correlation, but there is some caveat in this features. Like for an example, if you take the jet of the energy, these are directly related to the polarization, right? So in principle, you cannot use this jet features, right? Also, like pions and kaons, to use them as a feature, you need to be able to distinguish them, right? But in the very, like let's say you are working with a 250 GeV or a huge energy, there's the distinction of the pions and kaons remains very elusive. So for that, what we did was we simulate 3 different data sets. Okay, this 0 corresponds to unpolarized beams, and minus 0.8 plus 0.3 is like the electron beam is having 80% left beam polarization, and similarly the flip polarization at 250 GeV. So the architecture of N and is we construct 3 hidden layers with number of nodes 100, 50, 25. Activation ReLU, output sigmoid. Loss we use binary cross entropy, optimize the atom. And if you see, so these are the plots. If you see like the rate one, if you see the first panel, then the first panel is constructed like in this way. The training, rather let's say the test set has been used as the unpolarized data sets, and the training has been and the test has been done on 3 different models. Okay, so and similarly for this minus 80 plus 30, and this one.
Add here. Yeah, so what we are trying to do over here is that the ANNs that were trained at 3 different data sets, we want to compare each other. That trained on one data set, let's say unpolarized, and test it on the data set that is polarized initial beams, and see if the efficiencies are different. So they are very much overlapping. And when you see this, the Gaussian distribution of efficiencies that are generated are like, you take a set of test data and don't test your model on all of it. You take a randomly generated 60% subset of your test data and compute efficiency of your model, and you do it 1,000 times for all shuffled data. Like you shuffle it, take 60%, shuffle it, take 60%. Basically, you are taking 1,000 times a random subset of your test and seeing how your network works, and then estimating that what is the variance on your efficiency. Instead of quoting just one number, we try to see how it is distributed under this procedure to capture the, if you have a different test data, how will your efficiencies will vary. And then that is for one particular kind of test data. Now you have one trained model, a certain kind of data, and you test it on other kind of data, which is generated using different initial conditions. And all what we are trying to show over here in these 3 plots, that it doesn't matter. The efficiencies are very comparable within the statistical variance. So we could have used any of the 3 models that we trained. And purpose of this particular cross-validation is to see that, is my model learning about the polarization itself when I'm doing the flavor tagging? Because if my model learned about the polarization, that means I cannot use it to measure the polarization. So flavor tagging procedure must be factorized. Okay, it should not depend upon the jet energy because jet energy is directly correlated to the polarization. Should not depend upon the initial state beam polarization, which decides the final state W polarization. So basically what we are trying to make sure is that our model has learned flavor tagging rather than any other things that happened before in the jet. So it's only learns, can I tag the flavor accurately? And the flavor tagging is not absolute, because what we are doing, the two jets coming from W, we are comparing with each other and asking which one of them is, say, up type quark. I don't care about up or charm. Okay, I don't care about down or strange. I care about up versus down, because that all is required for this particular process. Okay, so I give it over to Amir. Yeah, please proceed.
Yeah. So yeah, as Ritesh had said, the whole mechanism of tagging remains blind to the beam polarization, right? So, and we use our training model that we trained with the zero beam polarization and tested with a data set with increased energy. As you can see, these results are for the 250 GeV, and we tested with the 500 GeV, and as you can see, these networks did a fine job, right? The classification accuracy is around 85%. So basically, like I think most of you agree, like with this flow chart, right? What we do is we have some model, right? Any model. We pass it that model to some event generator. From that event generator, we get some matrix element events, and we hadronize them, right? So uh, after hadronization, those final particles has to be clustered into jets. We usually do via fast jet. After the fast jet, the truth leveling of the jet becomes very important. And in our case, what we used was the geometric distance of the initial quarks to the final jets. And then those data are passed to ML network, and you get your, whether it's the upjet and downjet, as Ritesh already said. We don't care about individual flavor of the jet. What we care about is whether the jet is of the up type or the down type, right? Because we are looking into the WW production jet. So after that, what you do, once you have the tagged events, what you do is you construct your observables, and then after constructing, you do your statistical inference. Professor Tomaso, like he talked in details what you have to do and what you don't have to do, right? And I think Dr. Sunanda also talked about this part, right? And this is, a brief overview of the proposal. So what we are thinking about is we are trying to translate our study to the VVJet study in the LHC. And earlier study was done in the context of ILC. It's very clean, whether but LHC is quite dirty. So we have to be able to discriminate WW, WG, ZZ events, right? Construct features which are more collider efficient. Like we were using pions, kaons, and I've said there are some caveat on that. And we'll be developing different kind of ML models that we learn here, right? GNN, ANN, BDT, whatever you like. And we'd be building a tagger for discriminating this thing, WWWG or GZ. And then once this has been tagged, we'll go deep and we'll try to flavor tag the content of it. And we are also planning for a full detector simulation, right, using maybe Geant, which may take time. So, these are just some outlines, but we can obviously add more and more stuff in it. While having a longer discussion.
And okay.
Yeah, so just again, to add one thing, perhaps we should have said it before. So here, everybody talks about new physics. Yes, there is a new physics, and the new physics over here is the anomalous triple gauge boson couplings. So standard, so there's a lot of interference effects and all these things over here, which briefly was talked by Aishik. So yeah. And here, when we move our analysis to LHC, we have some more challenges, but even before that, when we presented our result for ILC, we presented the best one. Actually, in our paper, we don't have the best one because there we only looked at those observables which does not distinguish between pion and kaon. But in ILC, there are some detectors which are now promising that yes, you can. So in the second analysis, we did include that what is the change we will get or improvement we will get if we include those features in our analysis. Okay, so it is multi-level, like what are your features depends upon what are your detectors. And of course, when we go for CMS, we have to go back to that we cannot distinguish between pions and kaons, okay, or protons for that matter. All the protons will not come over here. And then do the analysis. And here additional things, task would be there that we have WW, WZ, and ZZ channels. And so polarization observables are different accordingly. And just to mention that when I'm talking about W, I only care about up versus down. I don't necessarily care about exact flavor. And when I'm talking about Z, I care about the distinction between which is quark versus which is anti-quark and not which flavor of the quark. So I don't know if we will be able to do Z at all, but this is an attempt to see what one can do over there. Yeah.
Ritesh and
network is all about finding certain efficiencies and all that. And yes, the final result, so we don't feedback. You are right. Okay, we don't feedback. So we will quote that, okay, this much, with this much accuracy, we improved our limits on various anomalous couplings. Okay, it would be nice if there was a feedback, but that's too costly, as you can understand, right? The whole thing as a one network, because every step, you first train this part, get the statistical inference, then you feedback that no, this is not. So that for that, perhaps we have to depend upon what Professor Tomaso said about the differential programming. So that would be a meta machine learning thing, which is if one of you want to do, I will welcome. But I must also admit that I'm certainly not the expert to guide you in any which way. We will support you with providing the data if you want to proceed on your own. We'd like to be very closely associated with you because we also like to learn those things. Yeah.
yeah.
And when it comes to up and down, the actual significance is pathetic. So C and S is where we gain. Yeah, up and down we don't. Okay, and then you can also say that QCD also don't distinguish between Q and a Q bar. Yes. Right. So some other jet observables like something called jet charges and all these things one has to involve. Okay, which are weak classifiers. And then we can have, for different values of alpha, we can have more than one weak classifier in a hope that we can capture some of those things.
Yeah, so for C and S, mass is significantly different, so you can have some.
Yeah, there is a difference. And also, if you have available to you the pions versus kaon, this efficiency is really gross. Yeah, if you don't have, still you manage 70%, 75%.
But that will significantly depend on the Monte Carlo simulation of your jet.
Yeah, we did try the different tunes of Pythia and varied it, and it
was invariant.
Yeah,
invariant of the tuning.
Yeah, it's invariant of the tuning that we figured out. What matters within ILC is fine, not a problem. The translation of this analysis into LHC is going to be a big task because jet clustering itself might give you a lot more things from the other side. Okay, and if there are annular effects and all that stuff, so those things are more concernsome than the things you are saying. So because there will be jet variables, okay, which are lesser used because people want to measure the jet charges, and those are very weak classifiers. Okay, but as we know from experience that you use bunch of weak classifiers, you can kind of make a good classifier. Yeah. Thanks.
Any more questions? Okay.
Okay, thank you.
So
Thank you.
you know who the next speakers are. Okay, so it's Vishal and Partha.
Good morning, everybody. So after 2 weeks of preschool and this extensive, more than 1 week school, you have learned rigorously many different techniques. So now it is more exciting time where you are connecting those techniques with some of these favorite stories, basically what you love to do. So here I will talk about one such story. Basically, it is about this vector boson fusion search of Higgs using low-level feature data. So you have heard this reference of jet tagging, flavor tagging so many times. In that category, basically this is, you can tell this is a event tagging, some kind of event tagging based on its characteristic. So what is the special characteristic of vector boson fusion? So it is very general. Although I am talking about Higgs, it is actually most of the statement I am talking is very true for the BSM search also. So vector boson fusion was proposed long back for heavy Higgs search. As you see in this plot, it is a Higgs mass and this is the coupling. These are the four Higgs channel basically. Upper one is the gluon-gluon fusion Higgs channel. As you know, it is the highest cross section for Higgs search. The second one is the vector boson fusion channel, which is order one order of magnitude smaller. So why at all look at it? So initially, that's why initially people proposed that probably at heavy Higgs it will be, that time you don't know this where we will come up with this Higgs mass. So it was proposed for the heavy Higgs, but afterwards people realized something fascinating about this vector boson fusion. As you saw, as you check here that it is not only this one order of magnitude smaller than this gluon-gluon fusion, this uncertainty of coming from the QCD is much larger here in gluon-gluon fusion. Even in the next to leading log, you have so much uncertainty in the gluon fusion. Whereas vector boson fusion in the next to leading order itself, it is a scale uncertainty is around 10%. It is not about Higgs, it is about any BSM search you do, you will do next to leading order calculation, you will get around 10 to 12% in VBF channel. So it is very robust, very stable channel. You measure those one and you can actually statistically more stable calculation you can do. It has a very particular event topology. So this is the proton collisions. So one of the parton from the proton, they produce some kind of weak boson. Here it was shown with W boson, and they collide, they produce this product, Higgs product. In BSM search also, there are some BSM product can produce from there. And they produce, Higgs will eventually produce some Higgs decay product. So essentially you tag these two forward jets This is forward. Basically, they are in forward region with a large rapidity gap. So these are all the features of the vector boson fusion. And there is a very interesting characteristic because there is no color connection between these two lines. There is no color correlation between these two. So you find this between these two forward jets, central regions is more color neutral. Color neutral means less jet activity. And within this color neutral region, this Higgs decay product you will find. So characteristically, you have to find two forward jet with large rapidity gap. They have a very high invariant mass because of this large rapidity gap. And your decay product from this new physics or Higgs will be in between them in a color neutral state. So this was found long back, and then it was realized that it can be very important. And it became important when LHC started. We have seen not only this gluon-gluon fusion, actually vector boson fusion started giving a very sensible result. I will talk one of that result. So as I already discussed the topology, here you see this eta phi plane, tag jets are here, and central region where is the green shaded is the kind of less jet activity, and your Higgs decay products are here. Now, if you look at this typical backgrounds and signal, as I told that between these two tag jet, there are less jet activity. This is one sample event, but over the events, many events you can test that one. Here in the background, you will start getting lots of jet activity because of this color connection. Probably you understood this fact. So now, as I told that VBF become important some of the searches. For example, VBF is the most sensitive channel for invisible Higgs search. What happens that if Higgs goes to invisible, so that means Higgs is some way connected with the data between them, less color activity, and there is nothing. That means you will find those nothing through some missing ET signature. So VBF gives the most sensitive bound, upper bound of branching ratio, Higgs going to invisible. So Higgs to invisible branching ratio upper bound given by VBF, which is much larger than this bound given by Higgs by the CMS or Atlas, is much larger than the SM prediction. SM predicts something like you produced Higgs going to ZZ and Z going to neutrinos, and that is much less than 0.01%. So, but if you see this collider bound is very large. This is somewhat old data. I just, it was from our paper we analyzed, so I just stick with this one. This is 36 femtobarn inverse. That time, this upper bound of the Higgs going to invisible limit was 22%. You see the difference between 22% and 0.1%. This difference. Why it matters? Because lots of dark matter models rely on this Higgs portal dark matter. So all of them pass through because of this gap between these two. So whenever you have a model, you say that, okay, it is below 22% branching ratio, so it is valid. As soon as you reduce these to somewhat 2% or 1%, lots of models will rule out. So it is a very important channel or very important thing to look at how you reduce this upper limit of this branching ratio. Whatever data you have, you got this one. So this is actually not the CMS data. We reproduced with this CMS analysis. Exactly, we generated that signal background and we reproduced, and we got almost the same 1 sigma, 2 sigma limit with this median expectation value of 22%, slightly better than the CMS because we don't have systematics. Nevertheless, so now we start asking question that why this VBF channel, what special about this VBF channel? So probably now you realize that the specialty about VVF channel is the radiation pattern. So apart from these two forward jet, how additional radiation is happening, that radiation pattern is important. And all those variables constructed so far, what this CMS also utilized, is based on this characteristic. So that's why they this feature of this rapidity gap and neutral zone between them is actually valid. So we tried to see whether any deep machine learning framework can look at this event feature directly from the low level data and try to work on the betterment of this limit. With this same data, we started with this same data, which gave us 22%, and we try to look at this only low level data, no event reconstruction, no reconstruction of jets or anything. Just look at the calorimeter data and try to see whether we can improve over this analysis. So that is the thing. So here we have seen that directly with this calorimeter pixel data and with this CNN kind of network, you can improve 3 orders actually by the same data. So you can give a upper limit around 7.5% from the 22.5%. So this is based on a couple of papers here with Vishals and some other student and Arun, our friend Arun in CMS. So this is the classification of event feature through CNN. So I hope you understood this philosophy, and this is not very special about Higgs only. It can be applied to any BSM scenario or Higgs going to any other decay products. Here we propose to look at the decay product of H going to BB bar, which is the highest branching ratio for Higgs, and try to study some other decay channels of this Higgs by testing different modes like with CNN and graph neural network. Both of you learned during this school. So I hope that that can be interesting to go forward. This first one, since we have analyzed already, we have some idea how to move forward and what we expect from that. But this one is somewhat new. We will also learn from this experience. Thank you. So here are some poems. You can take a mic probably.
So in your analysis of BBF, have you considered the interference with? Have you considered the interference with like? Yeah, I mean.
So actually in the next slide, so if you want to know details, what are the signals and backgrounds we have done, some of this next slide we have to go. You will see these are the backgrounds.
No, but you can have 3 boson production, right?
So in our that example, Higgs going to say some chi bar, which is dark matter candidate. So in that specific example, what we have done.
Okay.
So here you have a 2 class of background. One class is kind of mimicking this signal, like this electroic vector boson fusions, and some of the QCD type. So there is no direct interference between them.
Okay. Yeah. Thank you.
Not same data. This is a different channel. So here, somewhat you can already ask this question. You could have been asked this question that you talked about this central region with a less jet activity. What about this BB bar? How it will spoil that one? Those things, those questions can come, and that is things to notice here. Those things will change. Equal images. Yeah, so yeah, right, at that time we used only one image data, and that was actually enough to do that one. Probably now you can actually go more specific. You can actually use multiple image data. That also.
We pad the image actually. So you are talking about the cylindrical geometry. We pad the image and do that. But you don't need to do that for graphs. You can have a circular graph.
Yeah. Huh? Yeah, leading jet. So, acha, PT range.
80 GeV and 40 GeV, I think, the first and the second. It's there in the, yeah.
Yeah, I think this one, yeah. So basically we took the what CMS started with. We started with that one, so we reproduced their result, and same data we used. Yeah. Yes. Yes. That can be, yeah, that I was thinking.
We
yeah.
tried, but it gave the same performance.
Yeah. So somehow when it is recognizing, it knows this feature.
We took the first 4 most dominant backgrounds.
Yeah.
Others are there. But
we calculated all of them, but which is more dominant after these first selections.
Okay, so hi everyone.
and thanks to this organizer for inviting me. So this is the topic that I'll be discussing. So ML-based top tagging and its application to BSM. So we have done some ML-based top tagging. I'll discuss that. And the main emphasis of this project will be its application to several BSM scenarios. So you all know what are the importance of top tagging, why we are interested in top tagging. So if we have a top which has low PT, then the decay products of that top will be resolved. If we have high PT top, then the decay products will be boosted. So we will have a collimated beam of hadrons that can be tagged as top jet. And it can be easily distinguished from this quark and other light quark jet because they will have some non-trivial structure. So these are the things I think everyone knows in this school. But the question is why you are interested in top tagging and use tagged object to construct the events at LHC. So there are three main motivations. First of all, we have not seen any BSM at LHC that automatically tells you that the scale of new physics is high. So from that high new physics scale, if standard model particles are coming as a decay product, then they will be naturally boosted. So it is natural to use the boosted topology. Second is if you have a very good tagging efficiency, you reduce QCD background. And most importantly, top and W, there are two possible decay modes. Either they can decay leptonically or hadronically. So leptonic decay comes with missing energy. So you cannot reconstruct their momentum. So that will create problem in the final event reconstruction. But in case of hadronically decaying top, all the particles are visible. So you know the whole momentum of the top. You can reconstruct your events. So there are different machine learning based. So this is, yeah. So there are the different ML based top taggers. A class of top taggers use high level features like the jet mass, M subjectiness, B tag, number of tracks. These are the widths of tracks and calorimeters, etc. There is a long list of such observables. And there are some top taggers which are built on low level features like the form momentum of the jet constituents. So convolutional neural network, graph neural network, and there are several others. So I'm just talking about these two because we have done work on these two. So these are the two different classes of top tagging algorithms. Now what we have available for these algorithms. So for high level feature based top taggers, we can use BDT, and this is very simple to use because this is available in the root package, so you can directly use this algorithm. However, for the low level feature based top taggers, we have different kinds of models. As I discussed, CNN, GNN are example. So in this work, what we have done, we have considered this simple class of models. So I'll explain what are these. So this BDT represent the model which we have used the high level features to train a BDT. CNN, GNN are the low level feature based model. And this callow and track, these two quantities represent what are the data set that has been used to train those models. In this callow, we have used calorimeter tower data. We do not use the information about the track. Or in this track, BDT track or the CNN track or the GNN track, we have used data from tracks as well as data from towers. In fact, actually we have used the distribution, the distribution of charge and neutral hadrons inside of hadjet. So that's the important feature that we have introduced in this track-based classifiers. After introducing these simple classifiers, we have defined a set of composite classifiers. So at the score from this low-level feature-based classifiers is used as a high-level feature in the BDT along with the other high-level features like the invariant mass, subjectiness, etc. of the BDT. So these are the set of classifiers that we have tested, and we try to find out the classifier which performs best in terms of classification efficiency as well as in terms of reducing the systematic uncertainty. Because we are using the low-level information, so it depends heavily on the jet modeling in the Monte Carlo simulator. So we need to understand that which model reduces this dependency. So this is a figure I have shown to tell you the advantages of tracking data. Why we think that this tracking data would be helpful to distinguish a top over QCD background. See, when a top decays into 3 quarks, it has 3 structures resulting from 3 quarks. This is the important characteristics of top fat jet, which helps us in distinguishing top quark. A QCD jet can mimic a top quark if a radiated gluon from the jet gives you a structure inside the jet. So that will ensure, that will give you another structure. You can have some more structure and that will mimic a top quark, an image of a top quark. Now you see that all the jets inside, all the subjets inside a top fat jet is originating from quark. The origin is quark. Whereas for QCD jet, it is most likely that the origin of the subjet inside a fat jet will come from gluon, right? Because gluon splitting is more than quark splitting. So inside that gluon jet, the probability that a subjet is coming from a gluon, hadronization of a gluon will be more. And we know that from previous literature, that tracking information can help distinguishing quark and gluon origin of a jet. So that's the feature we are trying to utilize. And these are the results. I will not go into the details of this result. Maybe in the afternoon session, when we will have the project discussion inside the group, we can discuss. So roughly, so these are the results. So this solid line represents the data set which has been generated using Pythia, whereas the dotted line represents the data set which has been generated using Hardwick. So these data set, we want a comparable performance between these two data sets because we do not want huge systematic uncertainty. So you see that these are the performance of simple calorimeter based classifiers. This is BDT, CNN, GNN, and these are the performance of track based classifiers. So these are the list of numbers at 50% tagging efficiency. So you can see that track based classifiers perform significantly well compared to the tower based, calorimeter based classifiers, which is expected. So in the next plot, we show the performance of composite classifiers which are GNN based. Oh, sorry, I missed one, which are CNN based. I will not discuss, go into details. So these are the same thing as the previous one. Here I have something to discuss. So these are the composite classifiers based on GNN algorithm. So the point I want to emphasize is that, so this is the performance of GNN based simple classifier, calorimeter based. This is the performance of GNN based classifier which are trained using data which includes the information from the track. So you see significant improvement. This is the first point. You see that these bracketed quantities, bracketed numbers are basically the background rejection coming from Hardwick generated data set. So you see for a calorimeter trained GNN, the uncertainty is small. Whereas for a track trained GNN, the uncertainty is huge, it's about 40%. This is because of the fact that when you use calorimeter data, the detector dependency is smearing out because of the finite resolution of the calorimeter. Here we are using track. So tracks are much more resolved objects, so you have huge systematic uncertainty. Now if you look at this combined classifier which performs the best actually, so if you look at this classifier, the systematic uncertainty is small here. So we combined BDT with the score of track-based GNN, we obtain this performance, but the systematic uncertainty is also reducing. So this is because of the fact that in case of a composite classifier, the score is not the only high-level feature that has been used by the classifier in the discriminating task. So there are other variables which the classifier also uses. Right, so and these variables, this invariant mass, these tau variables, B tag and other variables, these variables do not come with significant amount of systematic uncertainty due to the hadronization model in the Monte Carlo generator. So these actually reduces the score. This actually reduces the systematic uncertainty. In this case, when we only use the score in the discriminating task, we have huge systematic uncertainty because we are using relying 100% on the score. However, in this case, we are relying on all these variables. Only we are relying on a score only on in 35% of the event classification. So that actually reduces the systematic uncertainty. So this is an interesting thing. This can be used, I mean, a combination of variables which are some of which are sensitive to the Monte Carlo generator and some of which are not sensitive to the Monte Carlo generator. They can be used in a combined way to reduce the systematic uncertainty. So this is not the result that we are trying to found, but we obtain this result that systematic uncertainty can be controlled in composite classifiers. Now, these are the efficiencies. In this slide, what are the efficiencies that I have discussed is the efficiency of the classifier. So classifier efficiency depends on two quantities. First of all, the classifier itself and how we prepare the training and testing samples. Right. So if we give a very pure training and testing sample as input, classifier efficiency will be high. But what we need actually is the top tagging efficiency. That means if we have a boosted hadronically decaying top, what is the efficiency that top will be tagged as a top quark? So that is calculated, that is shown in this plot. We have done this analysis for two different values of reconstructed radiation, 0.08 and 1.02. So you see here, so 0.08 radius jets shows a better classifier efficiency. However, in case of actual top tagging, the 0.08 radius jets do not show better efficiency. So that tells you that we should take different values of reconstruction radius in different PT regions. So based on all this Okay, so based on all these observations, what we did, then we developed 6 different models in PT range between 500 to 300 to 1.5 TeV. We used different reconstruction radius. For example, for first 2 PT bins, we used reconstruction radius of 1.2, and for other PT bins, we used reconstruction radius of fat jet of 0.8, and we obtained these rejection factors. Classifier for classifier efficiency 50% and this rejection factor for classifier efficiency of for top tagging efficiency. This is not classifier efficiency, for top tagging efficiency of 50%. So you see that actual top tagging efficiency is significantly different than the classifier efficiency, because in this case we are not using any truth level tagging criteria. So we are passing all the generated top sample into the classifier. So that significantly reduces the performance of the classifier. But still we have significant enhancement compared to the existing literature. So the idea of this project is, so there are 2 points. First of all, we can contribute in developing the classifiers. So there are different things. For example, there is a need for a detailed systematic uncertainties about the classifier. So we have pointed out that how we can reduce the systematic uncertainty. So a detailed study, we can do a detailed study. Then we have seen that the performance of the classifier actually goes down if we go to higher transverse momentum. So to fix this issue, what can be done, that can be studied. We can use variable radius jets. We have used fixed radius jet, but different radius for in different PT range. We can remove the problem by using variable radius jets. So how the classification looks if we use variable radius jets. So that is also a study we can do. And the application to BSM searches. So the application of boosted top tagging in BSM searches is huge. So we have a boosted top tagger, and we have developed the tagger for all PT range. This is a low level top tagger. So it can be used in different searches for different supersymmetric models. For example, supersymmetric model gives you boosted top from gluino decays. If we have a RS graviton, that will decay to top. Yes, we have simulated the data in PTIA and Harvey, 2 sets of data we have developed. Then we simulated it, then we hadronize it in PTIA and Harvey. Then we reconstruct the object in Delphis. And from there we use our code.
This is doing at the Delphis level.
Yes, Delphis with Atlas card.
And the tracks and all these things you take from Delphis.
Yes.
Yes.
Oh, so we did something. So Delphis tracks actually comes with the mass of the particle. Okay. So if you use energy momentum conservation from the track 4 momentum, on the track 4 momentum, you get back the mass of the particle. Okay. So we actually remove that information. We mask that information. We use energy as the absolute value of 4 momentum. Okay. We only use the charge information.
Okay.
Okay, so
Building only.
we mask the mass information because that will give us more dependency on the Monte Carlo simulator. And also we need to introduce the mistagging efficiency because if you can, I mean, Delphis do not consider the mistagging and tagging of pions and kaons. So a pion can be mistagged as kaon, a kaon can be mistagged as pion. So to avoid all these things, we just mask the mass information.
Thanks.
I have few questions. So if we don't have time, then I can discuss with him later on.
Just ask one, then we'll discuss this.
Okay. So regarding this, let's say when you compute the high level features from the jet, okay. So do you consider varying different parameters in that, or you consider some fixed value? Because that has a very good sensitivity. For example, in subjettiness, there are some parameters that you can vary. And
no, we took the fixed value that actually literature uses. So that value we took. We do not vary those.
So yeah, so it has a very
for
good
jet
sensitivity
charge
that
and subjettiness, you can vary those parameters. Yes,
so that is one thing that you can incorporate. And another thing regarding this variable radius that you are talking about. So what kind of variable radius you are thinking of, by manually varying it, or?
Okay, so there are different ideas. I mean, in literature, you can find out how to choose a variable radius. There are different algorithms. So simply, you can think that you construct a bigger radius jet. Say a jet with radius 1.5. Okay, and then you demand that what is the radius in which 90% or 95% of the energy is deposited. Yeah, so that you can do, but that will come with some theoretical issues like collinear and soft divergences, etc. So that can be a brute force method to have a variable radius jet.
So in your estimation of this background rejection, you quoted the numbers and you were talking about uncertainties, but did you do it in
No, we do not do it for all this.
No. What I'm asking is, did you train the network only once, or how many times did you train the network? Because there will be training uncertainties.
No, we trained the network only once. So only once with Pythia generated sample. Then we tested the result using Pythia and Hardwick generated sample. So this is what we did, and these are the numbers that we get.
And you use a fixed tune of?
Yes, fixed tune of Pythia. Yes.
I mean, I have a question on this slide. So here you quote two columns, like where the signal efficiency is 70%, one is 50%.
50%, yes.
And at that, I mean, I should compare the background rejection at the same signal efficiency, right?
Yeah, so these are the background rejection for different models. And these are the background rejection for Pythia generated sample, and this is for Hardwick generated sample, and this is a different set of data.
No, I mean, when I compare
the numbers in column.
Not in row,
not compare two columns.
No.
Oh, okay. I see. Yeah. Okay. Thanks.
I think we should stop here. We can go to the next one. Over, I think people can still ask.